The National Electrical Code and Underwriters Laboratories contain requirements for direct current distribution in residential homes. The National Electrical Code, specifically Article 690, covers general requirements for direct current systems. These requirements include voltage limitations, grounding practices, and overcurrent protection methods. Article 692 provides specific requirements for photovoltaic systems. These include wiring methods, circuit protection strategies, and the interconnection of the photovoltaic system to the utility grid. Underwriters Laboratories Standard UL 1741 is the standard for inverters, converters, controllers, and interconnection system equipment intended for use with distributed energy resources. UL 1973 is a standard related to photovoltaic systems. UL 9540 is the standard for energy storage systems. It is important to note that in addition to the NEC and UL requirements, local or state codes may also apply to direct current distribution systems in residential homes. It is always advisable to consult with a qualified electrician and local building inspectors to ensure compliance with all applicable regulations. The NEC and UL requirements are subject to periodic updates. It is important to refer to the latest editions of these documents for the most current information. When designing and installing direct current distribution systems in residential homes, several critical factors must be considered to ensure safety and compliance with relevant standards and codes. Firstly, voltage limitations are paramount. The National Electrical Code specifies voltage limitations for direct current systems to mitigate the risk of electric shock and fire hazards. These limitations vary depending on the application and location within the dwelling. For example, Article 690.7 outlines voltage considerations for photovoltaic systems, specifying maximum direct current voltage levels for different system configurations. Secondly, grounding is essential for direct current systems. Proper grounding provides a low impedance path for fault currents, minimizing the risk of electrical shock and equipment damage. Article 250 of the National Electrical Code provides comprehensive requirements for grounding and bonding, including specific provisions for direct current systems. These provisions address the sizing of grounding conductors, the installation of ground electrodes, and the bonding of metallic enclosures and equipment. Thirdly, overcurrent protection is necessary. Overcurrent protection devices, such as fuses and circuit breakers, are designed to protect direct current circuits from excessive current flow, which can result from short circuits, overloads, or ground faults. Article 240 of the National Electrical Code outlines the requirements for overcurrent protection, including the selection and installation of overcurrent devices. For direct current systems, it is crucial to select overcurrent devices specifically rated for direct current applications, as alternating current devices may not provide adequate protection. Fourthly, wiring methods are important. The National Electrical Code specifies appropriate wiring methods for direct current systems to ensure the safe and reliable transmission of electrical power. Article 300 provides general requirements for wiring methods, including conductor sizing, insulation, and protection. For direct current systems, it is essential to select conductors and insulation material suitable for direct current applications, considering factors such as voltage rating, temperature rating, and environmental conditions. Fifthly, circuit protection is mandatory. Photovoltaic systems, which often utilize direct current distribution, require specialized circuit protection measures to address the unique characteristics of photovoltaic power generation. Article 690 of the National Electrical Code provides specific requirements for photovoltaic circuit protection, including overcurrent protection, ground fault protection, and arc fault protection. These protection measures are designed to mitigate the risk of electrical hazards associated with photovoltaic systems. Sixthly, interconnection to the utility grid must be safe. When direct current systems are interconnected to the utility grid, it is essential to comply with the requirements of Article 705 of the National Electrical Code, which addresses interconnected electric power production sources. These requirements cover various aspects of interconnection, including synchronization, voltage regulation, and protection against grid disturbances. It is crucial to coordinate with the local utility company to ensure that the interconnection complies with all applicable requirements and safety standards. Seventhly, inverters, converters, and controllers are used. Underwriters Laboratories Standard UL 1741 provides requirements for inverters, converters, controllers, and interconnection system equipment used with distributed energy resources, including direct current systems. This standard covers various aspects of equipment safety and performance, including electrical safety, mechanical integrity, and environmental testing. Compliance with UL 1741 ensures that these devices meet recognized safety standards and are suitable for use in direct current distribution systems. Eighthly, energy storage systems need standards. UL 9540 is the standard for energy storage systems, which are often used in conjunction with direct current distribution systems to provide backup power, improve energy efficiency, or enable grid independence. This standard covers various aspects of energy storage system safety and performance, including battery safety, thermal management, and control system reliability. Compliance with UL 9540 ensures that energy storage systems meet recognized safety standards and are suitable for use in residential applications. Furthermore, compliance with local and state codes is essential. In addition to the National Electrical Code and Underwriters Laboratories standards, local and state codes may impose additional requirements for direct current distribution systems in residential homes. These codes may address specific aspects of installation, inspection, and permitting. It is crucial to consult with local building inspectors and electrical authorities to ensure compliance with all applicable codes and regulations. Finally, consulting with qualified professionals is crucial. Designing and installing direct current distribution systems requires specialized knowledge and expertise. It is always advisable to consult with a qualified electrician and electrical engineer to ensure that the system is designed, installed, and maintained in accordance with all applicable standards and codes. These professionals can provide valuable guidance on system design, equipment selection, and safety practices. In summary, direct current distribution in residential homes is governed by a comprehensive set of standards and codes, including the National Electrical Code, Underwriters Laboratory standards, and local and state codes. Compliance with these requirements is essential to ensure the safety, reliability, and performance of direct current systems. By carefully considering voltage limitations, grounding practices, overcurrent protection, wiring methods, circuit protection, interconnection requirements, and equipment standards, it is possible to design and install direct current distribution systems that meet the needs of residential homes while maintaining a high level of safety and compliance. The National Electrical Code Article 690 provides comprehensive guidelines for the installation of photovoltaic systems, including direct current wiring. It details acceptable wiring methods, grounding requirements, and overcurrent protection strategies specifically tailored for direct current circuits and photovoltaic arrays. This article is essential for ensuring safe and code-compliant installations. Article 692 delves into the specifics of photovoltaic systems, covering aspects like rapid shutdown requirements, disconnecting means, and signage. Understanding Article 692 is critical for anyone involved in installing or inspecting photovoltaic systems, as it addresses key safety and operational considerations. Underwriters Laboratories Standard 1741 sets the bar for inverters, converters, and controllers used in distributed energy resource systems. It establishes rigorous testing procedures and performance criteria to ensure that these devices can operate safely and reliably within direct current distribution networks. UL 1973 focuses specifically on photovoltaic systems, outlining safety requirements for components like solar panels, combiner boxes, and direct current disconnects. Compliance with UL 1973 demonstrates that these components have been evaluated for potential hazards and meet industry-recognized safety standards. UL 9540 addresses the growing field of energy storage systems, providing safety guidelines for batteries, charge controllers, and other components used in direct current coupled storage solutions. Adhering to UL 9540 540 helps to prevent thermal runaway, electrical shock, and other potential hazards associated with energy storage. Direct current distribution systems present unique challenges compared to traditional alternating current systems. Firstly, direct current arc flash hazards are significant, as direct current arcs can be sustained more easily than alternating current arcs. Therefore, proper overcurrent protection and arc flash mitigation strategies are crucial. Secondly, direct current voltage drop must be carefully considered, especially over long distances. Proper conductor sizing is essential to minimize voltage drop and ensure efficient power delivery. Thirdly, direct current grounding practices differ from alternating current grounding, requiring careful attention to ground fault detection and system bonding. Fourthly, direct current component selection is critical, as not all electrical components are rated for direct current applications. Using components specifically designed for direct current is essential for safety and reliability. Designing and installing direct current distribution systems requires a thorough understanding of electrical codes, standards, and best practices. Firstly, conduct a detailed load analysis to determine the direct current power requirements of the home. Secondly, select appropriate wiring methods and conductor sizes to meet the voltage drop and ampacity requirements. Thirdly, implement robust overcurrent protection and ground fault detection systems. Fourthly, ensure proper bonding and grounding of all direct current equipment. Fifthly, use components specifically rated for direct current applications. Sixthly, follow all applicable codes and standards, including the National Electrical Code and Underwriters Laboratories standards. Seventhly, obtain necessary permits and inspections from local authorities. Eighthly, document the installation thoroughly, including wiring diagrams and equipment specifications. Ninthly, provide clear labeling of all direct current components and circuits. Tenthly, educate the homeowner on the operation and maintenance of the direct current system. Regular inspection and maintenance are essential to ensure the continued safety and reliability of direct current distribution systems. Firstly, inspect wiring and connections for signs of damage or corrosion. Secondly, test overcurrent protection devices to verify proper operation. Thirdly, check grounding connections for integrity. Fourthly, monitor battery health and performance in energy storage systems. Fifthly, clean solar panels regularly to maintain optimal power output. Sixthly, verify that all components are operating within their rated specifications. Seventhly, address any issues promptly to prevent potential hazards. Eighthly, keep accurate records of inspections and maintenance activities. Ninthly, consult with qualified professionals for assistance with complex maintenance tasks. Tenthly, stay informed about changes to electrical codes and standards. Direct current microgrids offer the potential to improve energy efficiency and resilience in residential homes. Firstly, direct current microgrids can reduce conversion losses by eliminating the need for alternating current to direct current and direct current to alternating current conversions. Secondly, direct current microgrids can enable the integration of renewable energy sources, such as solar and wind, more efficiently. Thirdly, direct current microgrids can provide backup power during grid outages. Fourthly, direct current microgrids can improve grid stability by providing distributed generation and storage. Fifthly, direct current microgrids can reduce energy costs by optimizing energy consumption. Direct current distribution systems are becoming increasingly popular in residential homes due to their potential benefits. Firstly, improved energy efficiency because direct current eliminates alternating current to direct current conversion losses. Secondly, increased renewable energy integration by direct current enabling more efficient use of solar panels and batteries. Thirdly, enhanced grid resilience due to direct current providing backup power during outages. Fourthly, reduced energy costs through optimized energy consumption and self-generation. Fifthly, greater control over energy usage. Firstly, plan carefully. Secondly, design properly. Thirdly, install professionally. Fourthly, inspect regularly. Fifthly, maintain diligently. Direct current voltage levels in residential applications must adhere to safety standards to prevent electrical hazards. Firstly, extra low voltage direct current systems, typically below 50 volts direct current, are considered relatively safe for general use. Secondly, low voltage direct current systems ranging from 50 volts direct current to 1500 volts direct current require additional safety precautions such as insulation and overcurrent protection. Thirdly, high voltage direct current systems exceeding 1500 volts direct current are generally restricted to industrial applications and require specialized safety measures. Choosing the right direct current wiring methods is crucial for ensuring safety and reliability. Firstly, shielded cables are recommended for direct current power circuits to minimize electromagnetic interference and prevent ground loops. Secondly, twisted pair wiring can reduce noise and improve signal quality in direct current communication circuits. Thirdly, conduit provides physical protection for direct current wiring in harsh environments. Fourthly, cable trays offer a flexible and organized way to route direct current wiring. Direct current circuit breakers and fuses play a critical role in protecting direct current circuits from overloads and short circuits. Firstly, direct current circuit breakers are designed to interrupt direct current quickly and safely. Secondly, direct current fuses provide a simple and cost-effective way to protect direct current circuits from overcurrents. Thirdly, choosing the appropriate direct current circuit breaker or fuse rating is essential for ensuring proper protection. Direct current ground fault protection is essential for preventing electrical shocks and equipment damage. Firstly, ground fault circuit interrupters, or GFCIs, can detect small leakage currents to ground and interrupt the circuit. Secondly, ground fault detectors can provide early warning of ground faults. Thirdly, regular testing of ground fault protection devices is essential to ensure proper operation. Consider bidirectional direct current to alternating current inverters. These inverters can convert direct current power to alternating current power and vice versa, enabling seamless integration of direct current and alternating current systems. Direct current optimizers can improve the performance of solar panels by maximizing power output and reducing shading losses. Direct current load controllers can manage direct current loads efficiently, reducing energy consumption and improving system performance. Direct current energy meters can accurately measure direct current energy consumption, providing valuable data for energy management.